Yeah, you said. Yeah, can I ask something?
We were previously talking about like looser or FS or NTF.
Yeah.
Because I usually stumble upon these things. I mean, a class of that.
Yeah.
And they just tell me, okay, this output is code, oh yeah, it's faster. I didn't understand why it's faster or why it's.
So, yeah. It depends on how you're doing your output. And I suppose the thing is, even if you're just doing, a normal write to a file, the slowest part of your I/O is the disk. Okay? So if you have an application, and even if it's over a network, so if you have an application, and then it's going out over a network into a server, and then down onto it, so that sort of thing, right? And the slowest part in all of this is that. Okay, so if you're just writing a single, even if you're writing a single stream to a single disk, that's the slowest point. So if you move to something like Lustre, GPFS, or whatever, the point is when you get to this all of a sudden turns into 10 servers, each with lots of disks. And so even though you might only have one stream, it's being written to this and this and this and this and this at the same time. So, so if each of these is running at 100 megabytes a second, then if you're writing to 10 disks, you can get 1 gigabyte per second of transfer. Okay, so that's why it's always better to write to the parallel file system than to write to a local slash, like a local scratch or /10 or something on the node that you're running on. Because even though it has to go over the network, it'll be writing an aggregate on lots and lots of disks. And so the only way to make disks fast is to have lots of them, because each one is saying anywhere 100 megabytes per second, give or take. So, but then if you have 20 disks, then you're running 2 gigabytes per second, and also that's fast. So even if you just got a single stream, then that's why this is still faster, because the file system is taking your data and saying, this bit belongs to that block, this belongs to this block, and there you go out through different servers, down to different disks underneath that. So that's why really you're effectively getting the benefit of striping your write across all of these disks at the same time. Then obviously if you're doing this in parallel, then you have another application server, another application server, they all feed into this network. But then you still have the same thing of lots of things going to lots of servers, going to lots of disks, gives you aggregate reasonable performance. Where if you had just one guy talking across one network to one disk, it would all suck. So really that's what you're doing, just scaling up the overall aggregate bandwidth. That's why you should, even for a single write, like just doing F open, printf, and F close, you should still try and do it to usually to the parallel file system that's available to you, because it won't be any slower and it'll probably be faster.
When you use the structs folder.
Yeah, I mean if it's on the parallel file system, yes.
And then transfer them to the.
Yeah, I mean, and different places have different policies, right? I mean, the way we have it is that we have in our systems we have a fairly small home partition, but that's backed up. And then we have a fairly large project and a fairly large scratch, all on the parallel file systems. And so we let people put whatever they want, but on the understanding that if we need space, we're going to delete all the old stuff, or we'll just randomly delete things that are there. So if you really need it, take the stuff you need back to your home directory, but each person on their home system has a limited amount of space, and then people just copy it back onto their own workstations or their own group server or wherever they need to put it. So, but other places have different policies where everything is, it depends from place to place. Okay. The crack on. So what I want to do this afternoon is really to talk through some more of the features in MPI-IO to sort of give you some of the things where MPI-IO really becomes quite beneficial to use in your code. I mean, up until now, just literally doing sort of MPI file read and MPI file write gives you some benefit because at least you have the ability to write all of your data into a single file and then write your application in such a way that you can decide what data goes where from a single file. So that's at least beneficial. But really, the really good stuff comes when you start using things like non-contiguous I/O, using collective I/Os, using non-blocking I/Os, and all those sort of things that we'll talk about in the next sort of 45 minutes or so. So really, what we want to do is we want to look at a situation where you want to do non-contiguous access to your data, and by that I mean you want to read 2 bytes here, then skip over a bit, or about 2 ints, skip over a bit, read another 2 ints, skip over a bit, read another 2 ints, because of the way that the data has been written to the file by some previous applications, that the data has all been mixed up together. And so what you want is a situation where, if we go, it's easy to draw a picture. Where we have sort of a picture with our file, and we want this bit to go to rank 0, this bit to go to 1, this bit to go to 2, this bit to go to 3, and then this to 0, 1, 2, 3, 0, 1, 2, and 3. Right, so we want to have this sort of situation. So basically this, and this all go into rank 0, and then similarly there's a chunk of data that goes to 1, a chunk of data that goes to 2. So you could do this by doing do a read, then do an fseek, then do a read, then do an fseek, then do a read. Okay, so that is certainly a way you could do it. But if we actually want to look at, if we do this the right way, you get a far more efficient read of the data, because what you can do is you can set up one of these things that are called file views, which basically restricts the parts of the file that are visible to each different MPI task, so that each MPI task sees a file, only sees the bits of it that are its bits, but kind of sees them as if they're all joined up together. So it's one compressed, contiguous file rather than bits with jumps in them like this. And then the benefit of doing it this way is you're able to say, do one big read, which then the I/O layer and the file system layer can say, well, look, here's a big read, but actually it has to be handled by lots of small things. But I/O systems tend to like large reads and large writes rather than small reads and small writes, because there's an overhead associated with each read and write. And so if you only have to do one read that then happens to be handled by lots of bits, it's a lot easier to handle like that. So what is a file view? So a file view is a way of masking off bits of the file for each thing. By default, everyone can read and write all of the file, and that's the default. If I just do an API file open, then that's what happens. Anyone can read or write any value after opening the file. And on each one, everybody's offset is set to 0. The file pointer is set to the beginning of the file when they open it. What we want to do is restrict it. So we want to end up in a situation where we can actually enforce on the file system, at a file level and an MPI level, that rank 0 only sees these bits here and never sees any of these bits, never sees any of these bits, and never sees any of these bits. And even if it tried to, it has no way of accessing that data. So with the file view, you can actually set it up so that it can only see these. And then when it does a read, so if each of these, let's say each of these are 10 ints wide or something like that. If I do a read of 30 ints, what I'll actually read is I'll read all of those 10, and then all of these 10, and all of these 10 in one single operation, without having to worry about, oh, I have to skip over this bit, or I have to skip over some other bit, I have to skip over some other bit. So from rank 0's point of view, the file looks like it just contains this information and is a quarter of the size of the main size of the file. Okay, so the data is skipped over as if it's not there. So these are set using MPI file set view, and we use these 3 terms that are used to figure out what the file view should be. The term of a displacement, an E-type, and a file type. Okay, and so the displacement is the offset into the file where your bit begins. So that might be, in this case here, if it's just like this sort of file, rank 0's offset would be 0, or displacement would be 0. Rank 1's displacement would be 10 bytes, or 10 ints in. Rank 2's will be 20, and rank 3's will be 30. It might be bigger than that. Everybody might have a bit, because there might be some sort of header information, like we were talking about earlier on. So that might be there. So everybody might want to skip over that kind of information. But the displacement is the distance into the file before the view starts. Okay, so skipped over headers, but also skipped over aligns each MPI task on the bit that is their bit of the code to look at. Then the E type is what's called the extent of the data type that's stored in the file, and that can be a user-defined thing, or it can be a basic thing. So it can be an int, or it can be a type, it can be a struct, or it can be whatever it needs to be. And then the file type describes the chunk size within the file. So in this case here, we're talking about these being 10 ints. The E type of this data type is 10 ints, because that's the extent of data that I want to read here. And then the file type is 40 ints, because I want to have 10 for rank 0, 10 for rank 1, 10 for rank 2, and 10 for rank 3. So we effectively have a file type of size 40 ints or 160 bytes in length. The thing about the difference between the E type and the file type is the file type has to be a multiple of the E type, because you have to have, and there has to be usually will be a multiple that is a multiple of the number of MPI tasks times the E type, or unless you're going to read in these as sort of individuals along here. And so the file view does is it starts at this point here, we say for rank 1, and then reads this, and then this, and then this, and skips over all the bits in between. So we've kind of set that already. So how does this work in terms of code? Well, what we do in this case here is we've created a new type called MPI type contiguous, which we're just calling L type, or a local type or something. And we create this type to say a chunk of data that is 10 ints long. Then what we do is we resize the local one to be 40 ints long. Okay. So what we do is we say, even though the type is 10 contiguous ints, this is one of these things that's silly, or rather that gets confusing when you're talking about MPI to I/O in particular, and also if you're talking about RMA things about Windows and remote operations, is issues around the difference between the size of a thing and the extent of a thing. So the size of a thing is literally the size of the bytes that are in it. So if you have 2 ints, it's 8 bytes in size. And normally its extent will also be the same size. But if you've got a compound object, like a structure or something like that, you can have a difference between the size of an object and the extent of an object, because the extent is determined to be the distance between the start of one object and the start of the next object of the same type in linear memory. And where this becomes a problem is if we have, let's say, a struct. Normally it comes up that if you have a struct that has a double x, int, y, and char z. Okay, so that's 8 bytes, that's 4 bytes, and that's 1 byte. So if you do a size of this struct, you get 8 and 4 is 12, and 1 is 13. So size of is going to be 13. Okay, but if you look at what the extent of this object is actually going to be 16 bytes in size, because you have an issue here that when you're looking at doubles in memory, doubles have to be aligned on an 8-byte boundary. So effectively, you have to pad out the end of this to make sure that when you get the next card, so if you look at memory, you'll have your double x, you'll have an int y, and then you have a char z. So that's 8 and 4 and 1. But then I have to skip over 3 bytes before I can put in x2, y2, z2. Because this boundary here, because this is a double, has to be on an 8-byte boundary. So you have 13 and then 3 that are skipped over here. So the extent of this object is actually 16 bytes, even though the size of it is 13 bytes. Okay, so that's really what I mean usually by the difference between the size, how the size of an object is different from the extent of an object. The extent is as I said, it's formally defined as the distance between the start of one object and the start of the next object. Okay, so what we're doing in this case here is we're defining an object that takes 10 ints. Of course, now I've just update that diagram, which is what I wanted. We'll just redraw it over here very quickly. So we have our file, and we have so 10 ints here. So that's 10 ints that we want to go to rank 0. So we create an object that is 10 contiguous ints. And then what we do is we extend it, so we change its extent so that the object is actually 40 bytes. So it's actually 40 ints long. So the 10 that you want, plus the 10 for rank 1, plus the 10 for rank 2, plus the 10 for rank 3. So what you do is you extend the size of the extent of your object to be here. So now you can see that you have, this is going to A, B, C, and D, A, B, C, and D. You can see now the extent is from where the start of the first bit that wants to go to A, then the extent will bring you to the start of the next bit that wants to go to A. And similarly, if you move this up by 10, you'll see an extent matches B to B, C to C, and D to D as we go along. Okay? So that's what we do is we create this extended file type, or extended data type. We commit it then because now we have the file type being set to 40 bytes. And then we set the display, or the view on the file. So we're changing this file pointer that we previously opened. What we do is we change it to being where we want to start. So this is the offset of where we want to start. So in this case here, it's the displacement. So this is something that might be the header that everybody skips over the first 100 bytes or whatever it is of metadata, like the piece of the object. Plus, their rank times 10 times size of it. So it'll be the displacement, which will be on this part here first. This disk value. And then everybody will skip over their rank and 10 ints. So the first one will skip 0, the next one will skip 1, the rank 2 will skip to there, rank 3 will skip to there. So now everybody has a view that is 40 bytes long for the file type, but their local size is actually only going to be 10 ints. So you're going to come along and read 10 ints. And then when I come along and I read 20 ints, in this case here we'd say, I read this one and this one all in a single read, and there'll be no particular problem. Are we broken?
I should check if
okay.
it's working.
Oh, commercial break. Buy some Coca-Cola. It's good for you.
Okay.
Well, actually, what everybody should do at some point is while we're talking about advertising, if you really want to become good at MPI and sort of parallel programming in general, there's 2 books that I recommend to people. The first is a book written by a guy called Quinn, Q-U-I-N-N, who wrote sort of as an introductory sort of up to about middle level programming in MPI and OpenMP together, book by Quinn. And then the other one is the books by the guy Group, G-R-O-O-P. And he's one of the guys who's the chair of the MPI Standards Board. And every so often, I think they've just published the 3rd edition of using MPI and using advanced using MPI or something like that. And they cover basically everything. And it's effectively like the Kernighan and Ritchie of MPI is the books that this guy Group has written on. Yeah, basically everyone should have a copy of both of those on their shelf somewhere. Right beside your bed, and if you're really suffering from insomnia, open it up, and then 2 minutes later you'll be fast asleep. But the Iran Group is he's the main MPI expert for doing this. Anyway, so this is what we mean by doing these file views. And the thing to note is the file view is set then, okay? In the sense of there's no other way now to, once you've set a file view, you can't then access stuff that's being hidden by your file view unless you change the file view again to be a different view of the file. So actually the file view is set as soon as you open, a file view is actually set on your behalf as soon as you do an MPI file open on the file. It's just set so that the displacement is 0 and the F type and the F type is 1 MPI byte. So effectively, everyone can see all of the file with the default file view, and then by using the MPI file set view, you're just restricting down the amount of data that's visible within the file. The next important thing we want to look at in MPI-IO, this is really the one that will give you the most performance benefit, is using these collective IOs, which is effectively what it does is a collective reads and writes, force all processes in the communicator to do a read or to do a write at the same time. And then what happens is those writes are taken from the application layer, given to the MPI layer. So remember, going down our stack, given to the MPI layer, and then the MPI layer can optimize them in such a way that it takes lots of small little writes going all over the place and can actually sort of bundle them up into much larger and more efficient writes or reads, and then pushes them down into the file system where then they can be handled in a much more efficient way. And this is especially efficient where each process is doing this kind of thing of reading or writing different bits of the file. But overall, everybody wants to read the whole file. Okay, so if I set a file view, and then rank 0 goes MPI file read, and rank 1 goes MPI file read, and rank 2 goes MPI file read, and they all do an MPI file read for their own bit. Well, from the file system's point of view, if it did it that way, it would see one read for this bit, and then another read for this, and then another read for this, and then another read for that. If we did this as a collective, the MPI there can go, okay, we want to get all this stuff. Now let's smush it all together into one big read, saying, give me a big read from here through to here. And then when the data comes back to MPI can go, and yeah, you were meant to get this bit, and you were meant to get that bit, and you were meant to get the other bit, so that you get the full throughput from the file system level, and then MPI does the sort of the layer of handling edge. The semantics are pretty much exactly the same as the read, the normal MPI file read, except MPI read all turns it into a collective operation, but then the arguments are exactly the same after that. And it gives you a very efficient way of doing these collective reads and writes, especially when your data starts to get large. I mean, if you're in these sort of toy examples that we're going to play around with today, we're reading and writing tens or hundreds of bytes at a time. So no matter what way you do them, it's inefficient. But when you start to scale to hundreds of megabytes, to gigabytes of data that you're loading up from a file in one go, these collective operations will make, your performance will double or triple at least if you do these in the right way. It's very easy to write bad I/O, and with a little bit of effort, it's actually usually quite straightforward to convert that into reasonably well performing I/O. It's hard to get it to be super efficient and maximizing the bandwidth at all times. But even with a few sort of simple steps of changing to collective operations and things like that, you can really speed up the operation of your code. So one example I want to show you, and then we can look at it later on when we're in the lab this afternoon, is to look at this this matrix write operation. So what I have in this example is I have a matrix that are broken down into a block structure. So we have a 2n by 2n matrix made up of 4 n by n subblocks. Okay, so we have a situation here where we have my overall matrix, and then I want to distribute it such that so the block A is on rank 0, subblock A is on rank 0, subblock 1 is there, subblock 2 is here, subblock 3 is here. Okay, so this is all rank 0, rank 1, rank 2, and rank 3. But what I want is a situation where then this gets written out to disk. It's written out linearly, so it is literally from point 0, 0, then 0, 1, all the way through to, I suppose it's n minus 1, n minus 1, right? It's just written out in the normal way you expect it. So effectively, this line comes, this bit is first, then this bit, then this bit, then this bit, and so on, and then this bit, and then this bit, all the way through to that bit and that bit, in that order. Okay, I'm doing this C-wise, so it's going across the rows rather than down the columns. If it was a Fortran, everything just gets flipped, right, for efficiency purposes. But what we want to be able to do is come to a situation where we can manipulate our file views and our data structures in memory. So that's cheap and relatively efficient to do. And then when we actually get to do the I/O, just issue one call to do a write, a collective write, so that all 4 MPI tasks go, there's data, and that the data ends up being written out in such a way that it gets in the right order as things are coming along. So there's a function that's in the MPI standard that allows us to do this quite efficiently. This MPI type create subarray, which effectively allows you to create sub-blocks of a matrix on each location. You give it certain values that we'll look at that in a second. And then once we've done that trick of using this subarray function, we can then mess around with the displacements to get the values to the correct value, and then get everybody writing their piece of data in the right way. So if I dig up this MPI. Oh, sorry, that's still on the PowerPoint version. So there's this MPI matrix write that we can look at in a minute, and you can download it whenever you want. But basically, what we have in this piece of code here is a situation where we have each person, sorry, has an n by n sub-block of the matrix here. So here's my n by n, and I'm doing this in the way you're meant to do matrices, where you just allocate all of the data in one allocation and then mess around with your pointers it makes it easier, because what it does, it allows you to do a send of an entire block with a single send, rather than having to do packing and all that kind of stuff that might have to happen otherwise. And then now what I'm doing is, this is just actually putting in the values of the matrix in, right? It's not that interesting, but basically what we're doing is we're setting it up so that, I think, what should I say n to this? N is 4, okay. So it's a 4 by 4 matrix. So all I'm doing is I'm having my array, my matrix reads 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, 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 then to 65, 64, 63, 62, 64, and so on. Right? So that's what the numbers, the values in my matrix are. And like all of these things, when you're writing test code, put in values that you know what they're meant to look like into your test code, so then you can see is the right bit coming somewhere. So on rank 0, my sub matrix should be 0, 1, 2, 3, 8, 9, 10, 11, 12, 13, 15, 16, and 20, 16, 17, 18, 19, and 24, 25, 26, and 27. Should be the values that are in rank 0. And there's a similar sub-block for rank 1, similar sub-block for rank 2, and similar sub-block there for rank 3. Because that's what this messing around is trying to figure out what values they should be in. This is much easier to do if you just make a full matrix, and then you can subdivide it properly, or you can try and figure out what the value should be by having 2 indented loops and making a mess of things. But anyway, so this is just doing my initialization of the code, and then what we do is we look at our create subarray, and this is our key function here that's effectively pulling out these subarrays here. So we're saying each of these is a subarray of the full size. So where are my values here that I'm setting? So full size of the matrix is 2n by 2n. The local size is n by n, so therefore it should be pretty straightforward to figure out. So each one is full size. So the first argument is the full size of the whole thing. The next one is the local size of this. The starts, it just tells you which corner you start in for your overall global array. And then are we ordering them in C or Fortran style? And then what type of data do we have? So there is, and then we commit this new data type. So this creates us this subarray thing that says, I know I'm part of a bigger thing that's 2n by 2n size, but I only have n by n of them, and I'm starting in this particular corner. Then what we do is we play around with our offsets. And so this figures out where in the file, if I'm going to start writing, does the first element of each subblock go. So in case of rank 0, that should be the first thing that's written into the file because it's 0. And on rank 1, you want it to be number 4 is the first thing that gets written. But you want to write that 4. Where do you want to write that 4? At position offset number 4. So that's in this case here, you figure out the 10 times size of int. So that's okay. So that basically says we're going to skip over the first 4 ints and then write our value immediately thereafter. For rank 2, we want it to be this value down here, which is like x32 in this location here. So this should be 2 times n by n. So basically, I'll have skipped over all of this n by n and all of this n by n, and then start to there. And then what's the first place of this one? 32, 33, 34, 35, 36 is going to be 2 times n by n plus another n, because I'll have to skip over all this block, skip over all of this block, and skip over the first line of this value here. So basically, we're saying in our offsets, we have rank 0 is here, rank 1 is not far behind it, and then rank 2 is basically at the halfway point, and rank 3 is shortly thereafter. So both they'll all start writing in that particular way there. And then by having created this subarray here, you know, we've sort of effectively said how these things are related to each other by the fact that they're n by n subblocks of a 2n by 2n matrix. Then we open our file, so that's fine. So we can create it and do it in write-LD, so that's perfectly fine. And then we set the view on this file to be everybody views the data with my new type that I've created up here, and with the offset as appropriate, and we calculate it here. So basically we're saying, write your subblock as a subblock, so this subarray, starting at your offset from where the location is. And then, eventually, when we start to do I/O, the only I/O we actually have to do is open the file, set the view, write this new data structure out to the file, and then close it. And then the data is all there. So you don't have to do any loops around, you know, sort of print this line and then print that line and then print this other line. Basically, what you've done is by using the MPI data types that are available to you, you're able to really sort of hone in on the performance side of this and say, here's the data. I've told you what the structure of this data is. Now, MPI, you go out and sort out how to do this in the most efficient way and put the data where you want it to go. Okay? So if we compile this, hopefully I haven't broken much since I last wrote it, and then I run this. Oh, we're in Zen4. Got that out. I can't spell MPI run either. MPI run. We got a new file called matrix file, and it's 256 bytes long, which is good because that's 4 times, well, so they're 4 by 4 blocks, so altogether there's 64 things, and each of them are 4 bytes long, so 256 bytes in total, which at least seems like a reasonable value to have. And if I look at this using OD, you'll come to love OD if you start doing this on a regular basis. So what you can see is the order of these things as they're written out in the file is exactly the way we want them. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way down to 62, 63 as the values we wanted in the last point there. Then what this would allow you to do, I mean, if you wanted to play around with this code, what you could do is say, you know what, in the next time I want to, so I've created this matrix using this program, and I happened to work out that I wanted my block structure to be rank 0, rank 1, rank 2, rank 3. But the next time I might want it to be that rank 0 was all of the first, like they were just spliced in one dimension, it wasn't a two-dimensional decomposition of the thing. So you might say, look, let's take all of the first quarter of rows into rank 1, the next quarter of rows into rank 2, the next quarter of the rows into rank 3, and then the last couple of quarters of the rank 4. And you could just modify this by, as opposed to playing around with this subarray as sets of 2 by 2, you could have, you know, this is now as opposed to 2n by 2n is the full size. Instead, you could play around and say this is 2n times n over 2, or n over 2 times 2n, depending on which way you want to slice your data. And your file would just be still able to read it in, and then your data will be assigned to the different MPI tasks as it is appropriately set. And so there's lots of, I suppose, what's the right way to put it? yeah, I mean, there's a lot of flexibility in playing around with these, with the MPI data types and integrating those into your MPI IO that will give you the performance that you think you really want to get. One thing we could look at as well is there's this, there are these MPI info objects. And I don't know if people used MPI info objects much in their previous existence, but basically what they are is they're a set of hints that you can give generally to the runtime environment of your MPI about what you think the performance of your code is going to do. And they're passed as arguments to a lot of MPI2 and MPI3 function calls. And really the reason for that is when the MPI1 standard was written, they just sort of plugged in every argument that was there into the thing. So if you look at MPI all to all or something, there's just like 9 or 10 arguments to the function, and you kind of forget what you want to put in. And a lot of the time you don't want to put half of the arguments in, you're putting in zeros or nulls or something like that as arguments they don't really want to use. So the kind of is let's create these info objects as a set of key value pairs that allow you to put on in specific things. And if you don't put anything in, then the system just ignores it. But if you do want the system to behave in a particular way, you can turn on these key value pairs by putting a value in using MPI info set. So when you get an info object, you need to initialize it just initially to MPI info create using MPI info create, and then you can set the various info values by setting the key and the value this way. And then when you're that should be delete when you want to get rid of it, you can get rid of an info object as well by just getting on the delete. And so in MPI IO, where these come in is you'll see up here we have this MPI info null object here. But I could, if my system supported it, and this is one of these things where it depends on what your system is. If your system supports it, you can give lots of hints to your runtime to say, I'm going to access the file in this way, and I want the system to behave in a certain way. This particularly comes into play when you have things like MPI IO forwarders in your system. So if you're running on a large STI or BG machine or whatever, to say, collect all of my data here before it's forwarded here, collect data from this one here to go there. That kind of information. But actually, even if we don't pass in any information as an info to my file open, you can still actually get the default information that's in your system about the various things by playing around with this, by getting an info get the info object from the file handle, find out how many things are there. So info get n keys gets you the number of keys that are there, and then per key get the nth key out of this, and then you can get the info on that value, and then you can print out what the thing actually looks like. So if I just run that here for a second, I'll show you. So I'm just going to run this locally on my laptop for a second, because this is where I wrote the program the other day. MPI CC. So just put info.c. I run this as a.h. And so these are all the different keys that are set by default on a file object in MPI. So all I've done in this code, in this info.c, if you look at it again, is we just open a file. So we create one if it doesn't exist, but actually we don't write anything to it. We just create a file and then leave it. So it's not actually doing any useful data, but then it's getting all of the values that are there of the info file. And you can see there's lots of these sort of this Romeo layer is kind of the standard layer that's used in most MPI implementations for handling MPI IO. There are, as I say, vendor-specific ones from a few people, but you can sort of see that there's, I don't know what the CVE and stuff, but there's values around reading and writing. There's a buffer size, which is set by default to 16 megabytes. So I guess that's where earlier on we were kind of endlessly getting the same value back, even when we tried to open the wrong file handle, because there was still data, there was up to 16 megabytes of data available in the file buffer. It just kept reading back whatever the latest thing that was in that file buffer on our behalf. What else are there useful things? There's a read buffer and a write buffer size. Which one? Yeah. Well, what are you liking? Yeah, I don't know. I mean, that's like, I know they're there, but by and large, I mean, this is one of these things of most of the time, unless you're running on a large system, the defaults are fine. If you end up running on, on a very large sort of Blue Genie, K computerish type setup where there's, a very large structure and there's a very hierarchical file system, you may then end up wanting to set particular values of these to give hints back to the runtime to say this piece of data should be pushed that way, this other piece of data should be pushed some other way. But just so you know that those values are there. But the main reason that they're put into these, as I said, is mainly to reduce the number of arguments, because if each of these, if each of those values, sorry, if each of these values had to be an argument to MPI file open, and so there's an argument for buffer size, there's an offer for CD write, there's a value for CD read, and so on. MPI file open would then take 25 arguments as on the command like in your code, most of which you don't care about. So it basically allows us to hide all of these away from most people who don't need to see them, but in certain situations where it might be of interest, you're able to mess around with them and see if it changes the performance of your code. Last couple of things I want to talk about are our non-blocking I/O MPI. And non-blocking I/O is exactly as you expect it to be. It's just non-blocking versions of your reads and writes, so the same relationship between MPI send and MPI send is the same as between MPI file read and MPI file I read. So basically, you change your status object at the end of your read to a request object, like you do with MPI send, and then go off and do something else. And then when you need to check to see is your I/O actually completed, then you can use the usual MPI test and MPI wait functions to see if your I/O is completed. And similarly, there are, you could set up an array of request objects and then do MPI test all or wait all or whatever it is you need to do. So it's really useful to sort of be able to kick off an I/O in the background, let the I/O happen. So either loading up your file, but while you're loading up the data, then actually setting up some other, memory file structure, sort of another data structure in memory that you're then going to load the data into out of some buffer or whatever it is that you're going to do. So you can restart the transfer in the background. Because remember, what we're trying to do at all times is really trying to minimize that effect of the latency of going out to disk takes a number of milliseconds or up to the number of seconds if that's to go a long distance. And so if you can hide that away by going off and doing something else rather than sitting in a blocking file I/O, then that's great. So the usual things are there of once you've kicked off a file, a read or a write, don't mess with the data until such time as test or wait have told you that it's safe to do so. But other than that, they're pretty much exactly as expected to do. There's some support for non-blocking collectives. Some implementations of MPI have gone further down this route than others. So basically, you can do a read all begin with particular, basically the same arguments as read all, and then they should all collectively try and do their I/O as a non-blocking, and then do an end, and then do a read all end. But these don't tend to get used very, like a lot of these functions, they're there in the standard, and in certain circumstances it does make sense. It does actually make sense to try and use these if you can, because at this point here you're getting all of the benefits. Because you're getting the benefits of it being non-blocking, so you're not going to sit there and wait, and you get the benefit of being collective. So the MPI layer is able to aggregate all of the requests and send more efficient requests down to the file system. So then the file system can be loading up in bulk rather than doing lots of little sort of smaller size reads and writes. So it is actually the most efficient way to do it, but it's also the most tricky way to do it because you have most ways of actually getting in your way. You can either not be able to do it on all of the nodes, or you may not be able to do it, or you may not, or your data may be such that there's some dependency between your things, or that some people will return quicker than others and things like that. So it's just a bit messy. But this is probably the most efficient way if you can get it to work to do parallel I/O as we go along. The last thing I think we really want to talk about is, as a coding thing, is actually up until now we said when you do an MPI file open, everybody has their own file pointer. And that is true, and that is the file pointer that is then used for doing reads and writes, and especially when you're setting file views, you're still using this individualized pointer. But there is also a shared pointer that is shared across all MPI tasks on the communicator. And so if any MPI task makes a call to these MPI file read shared or write shared or seek shared, they change this global pointer. So I can read something on rank 0, then I can read something on rank 1, then I can read something else on rank 2, and it all push this global pointer along the file. The problem with that is that if you just did it with these, it's messy, because you've no guarantee of the order of things and which things are going to happen. So you have no way of being able to say, I want rank 0 to read from the global pointer first, and then I want rank 1 to do it, unless you put them into a for loop and you put MPI barriers in there and you make everybody have to wait until, those sort of ugly loops that everybody has written at some point. When you started writing MPI, and the first thing you did was, I want to print out everything in the right order. So I want rank 0 to print first, and then I want rank 1. And you have to put in a loop that went for I equals 0, I less than size of the world, I plus plus. If rank equals I, print MPI barrier, that kind of a thing. You have to do something similar with this. So there are collective operators that work on this shared thing that are much more useful, which is read ordered and write ordered. And what these do is they basically do a read or a write on the shared pointer, but in the order of the ranks on that communicator. So rank 0 will go first, then rank 1, then rank 2, and then rank 3. So if you want to play around the global pointer, it's most likely you're going to end up using these ones here. The global pointer tends not to be used as much, and the local pointers are far more flexible because each task has control of its own, and this is also what integrates with the file views. Well, they are there, so you can play with them if you want. So I guess to finish up, in terms of like talking, and then we can go and have another break, and then go back and try and write some more code later on, is just some general general hints, right? Don't do, well, if you're going to have, if there are, so I suppose actually rule 0, before any of these things are here, don't write lots of small little reads and writes. Okay, that's just generally bad. But if you're going to have a situation where you have to read a small shared file, so a config file or something like that has 100 bytes of data in it, or whatever, that says this simulation has 10,000 molecules and the cell size is this and the box size is that, and I want to lay out my MPI tasks as a grid of 2 by 4 or something. Yeah. So basic sort of config file level things. Then actually still the best way to do that is get rank 0 to read them in, and then use MPI broadcast to just spit them out to everybody else. If you go into shared I/O for these small little files, it's more overhead than you need, and it's just quicker to do with these. The question of how small is entirely down to what the system you're running on. And one person's small might be another person's medium at least. So do a little bit of experiments and sort of see, but generally if it's of the order of hundreds to a couple of thousands of bytes, up to maybe even up to a meg, it's possibly just easier to just read it once and then broadcast it or scatter or whatever needs to be done. Try to use the collective IOs where you can, because the best thing about this is it won't be any worse than if you don't use them, and it will probably be a lot better than if you do use them, because it will allow the MPI layer to reorder your IOs, aggregate them so that they become bigger transactions for the file system and lower layers to actually handle. So that's really try to use these collectives if at all possible. Limit the number of files in any single directory, so don't have a directory with 1 million files in it. If you need to write 1 million files, come up with some sort of hierarchy, so you have 3 or 4 levels of directories, and then the bottom level directories have 10 files in each of them, something like that. Because having one single directory that has 1 million files will kill any file system, not just a parallel file system. A normal file system will also be killed by that. So just be careful when you're writing your code that you don't accidentally go MPI run -n1 million, and then there are 1 million files created in your file system, because your systems administrator will hate you for the rest of your life. I think is really the way to put it there. And the reason for that is because every time you change a file in the directory or you change the directory itself, it has to scan through all of the metadata around that directory, and that just takes time, and you're loading stuff off disk and effectively wasting time, and it becomes very slow to parse through all these things. Do look at some other files, the sort of the higher level abstraction tools and file formats like HDF5 and NetCDF. If you have structured data that fits into that, or if you're part of a worldwide community that uses a particular file structure, learn about that structure, because then that makes you, part of that community and easier to exchange data with people. And nowadays, where all the talk of everything is about research data management and research data sharing and reuse of data and all that kind of stuff, in a HPC world where our data sets are really, really big, compared to everywhere else. Now, there's a reason we're called HPC, right? It's high performance, because we are, go bigger, go faster, go longer, we're just big, right? And so our data sets are the biggest data sets that are there. And so if you are not using the things that everybody else uses, then you're kind of in trouble because you're not able to share that data. And so somebody else has to waste in inverted commas. But we'll have to redo those calculations on their own system to enable them to be able to use the data. If you've already generated it in a shareable format that everybody can understand, I think is really what we're trying to get down to. And the last thing is, there's no solution, right? There's no one-size-fits-all magic solution that says, if you do this, your I/O will be amazing. No matter how many of these things you try to do, somebody will come up with a data set that breaks your code. Somebody will come up, or you will come up with a use case saying, oh, well, look, I'm going to use data this way, and lay out all my data because it's this sort of structure. Say, I have my matrices that I'm going to be loading, and I'm going to load them all row-wise or whatever. And then somebody will come along with the situation and go, yeah, but what if I have a matrix that is extremely narrow, but only has millions and millions of rows, but hardly any columns in each row? Then all of a sudden, your entire I/O structure may fall apart because somebody is using your code the way that you didn't expect to, or you didn't expect, and you may need to change certain things in it. So what works well for one may not work well for another. So do experiment, and do try and understand, or at least get a little bit of an understanding of how the underlying system is working. So if you're going to be working on a Lustre file system, read the documentation that your systems people have put together saying, this is a fast area, this is a small area set. Especially in Lustre, you can set certain characteristics on directories that make files behave in a certain order, that makes certain I/O performance good and certain I/O performance bad. It's not so much the case with GPFS, because GPFS is on a block level rather than on a file level. But understand the system that you're running on, especially if you're scaling onto a very large system where you have these sort of the I/O aggregators in the middle, because they will entirely change as you scale the number of cores you're running on. The pattern of which you're putting data into those collectors or aggregators will change. So get an idea of how your system fits together. Don't just blindly recompile your code and hope that it'll run. It'll probably run, but it may suck. So it's better to do a little bit of experimenting before you then sort of kick off your 6-week job and then find that 4 of those weeks were spent doing I/O when you had hoped it was only going to be a couple of hours. So really what we're going to do is we'll take another break and reconvene back over in the lab later on. And what we're going to do is we're going to play around with the matrix code, just so you can get a good idea of how these file views work and how we're calculating the offsets and using the various sort of data structures to play around with them. Then maybe a thing to do might be to read in a couple of matrices, so make a couple of square matrices, and then try and multiply them together using something like Cannon's algorithm. The reason Cannon's algorithm is useful is that you can't just read in the 2 matrices that you're going to multiply together directly and then just blindly apply Cannon's algorithm, because you'll end up multiplying blocks together that aren't meant to necessarily be blocked together. So we may need to do some changes to where your file views are and your offsets to be able to get you to read the blocks in the right location. Or alternatively, you can read them in and then just do a shuffle between all of these. We can play around with these. Since if we're going to do these and we're going to play around with floating point numbers, OD and hex dump aren't particularly good for floating point numbers, so it might be easier to just put them into GNU plot or Octave or Mathematica or something, or even write your own little serial program that just does the multiplication of your matrix correctly, so that you're sure that you're still getting the right answer. Mathematica is being okay. All the fonts and things don't want to work.
I've done it.
Okay. I'm talking about small matrices. And small dense matrix with square, n by n dimensions and real numbers, not complex numbers. And so keeping it simple as possible would be a good thing to play around with. And then here's a challenge that anybody wants to. Can you find a way to use MPIIO to make printing to the terminal window and reading things from the terminal window easier? I don't. Well, I'm not. I don't. But certainly, I don't think standard in. I think standard in is probably not possible. But there's probably a way to get standard out to work. This is the bonus points, right? For those who really have nothing to do with their evening.
I'll have to do with my
Ruin your life as well. Because as I say, like this is the thing that everybody does when they're first trying to do some IO and MPI, right? You haven't forwarded I left equals 0, I less than size of the world, I plus plus, if I equals blank. Print F stuff there, and then do a paragraph, right?
You say that like I don't still do that when debugging though.
Well, exactly. Everybody does this, right? Everybody writes code that looks like this. But I think there must be some way. Actually, I'm pretty sure there isn't. But I want somebody to actually do some work, right, to figure it out for me on my behalf. Is there a way? Because this would be really cool, right? If you could actually, instead of doing all this messing, go, MPI file write to standard out stuff, and then it just got written in the right order on standard out. Would be really, really handy for debugging things. It wouldn't really, because most of your file sizes, most of your data sizes are so large that if you're doing MPI, it won't work. But for debugging things that are small size, it might be more interesting than writing X for Yeah, don't do it over the weekend. Okay, let's stop and then meet up in the lab later on, and we can try and do something there. Does anybody have any questions on things that we've looked at so far? We let it all sink in a bit, and then maybe start writing some code. So I'll load, there's one last piece of code we need to copy up. There's info.c. And then Okay, so they're all sitting there. We'll meet up in a little while. Okay. Class dismissed.